Start with the first exercise then. So the first exercise, first of all, you can find it on TUVal here, and there. If you go on the TUVal homepage of the lecture, then the first exercise is now available, and you have the PDF here. So I already opened the PDF in the PDF here, and you have two problems. So every time there will be a problem will be discussed online. So
Hello.
Hello. You have a questions or?
Oh, no, sorry. I was just unmuted.
Okay. So the problem, I will solve it online live, and then you can find it on YouTube. And then there's a so-called homework. You can see here the homework. And the homework, you will have to go through the homework on your own and upload it into TUVal. So to upload it into TUVal, there is this homework one upload, and then you can just throw some files, and you have 2 weeks to do it. So here until 29th of March. This is only if you're interested in the exercise part of this lecture. So now let's move to the first exercise. So just as a kind of introduction, today we're going to be talking about the Z transform. So mostly you know that there's continuous time signal, so f of t or f of s in the Laplace domain, and we're going to study a little bit more about f of kts, which is a sampled signal, and f of z, so in the Z transform. So this refers to the first and second chapter, I guess, from the lecture notes. So mostly what you have already seen last week with Alexis. So the goal will be mostly to see how we can go from continuous to discrete time and from discrete time to continuous time. So how we can go from f of t to f of kt and f of s to f of z and vice versa. So just as a kind of initial kind of background, you should already have some background in what is continuous signal in time domain and in frequency domain. So for example, with y of t equals t, so just a ramp function, you know that you can express it into the frequency domain. Basically for discrete time, it's exactly the same. So we're going to see what y of kts means. We've already seen that in the lecture, and then how we can transform it into the z domain and what it means to be in the z domain. It's the same for an equation. So you can have an equation in the time domain, like second derivative of y is equal to u, and you can also transform it into the Laplace domain. In discrete time, it will be exactly the same. We'll be talking about the difference equation and then the Z transform. So don't worry if for now everything is not clear for the difference equation and discrete domain, because we're going to go through it. The main part is to understand that the Z transform is more or less the equivalent of the S, so the Laplace transform, but in discrete time. So once again, the goal is how we can switch from continuous to discrete time and discrete time to continuous time, because we know that the real world is continuous. So all the system you're working with are continuous, but usually the controller nowadays are discrete controllers. So you need to be able to switch from one representation to another. And also we're going to look at the Z transform properties and why we need to use the Z transform, but you're going to see that it's closely related to the Laplace transform properties. So now enough talking for the introduction that is already quite long. We're going to see the first exercise. So the first exercise that was proposed is that you have a continuous time signal, then you sampled it. So you just take one sample every 2 seconds, and you try to find the Z representation of this signal. So the first question that was asked is how to find the numerical values U of kts, which is obviously quite easy. So let's say that this is my continuous signal, so coming from 0 to 30 seconds. And so the signal discretization, the sampling time is Ts equals 2 seconds, okay? And so that means that I will just take 1 point every 2 seconds. The most important to understand here is that we have no idea what's in between those points. So if you only consider the sampled signal, you have no idea what's in between the points. It can be a straight line, it can be something else. Basically here, for example, once the signal is sampled, so I'm just going to show the MATLAB code now. If we just do it in MATLAB, so I just basically just plot the points one after another. So this is the sampled signal, and in the sampled signal, I have no idea what's in between the points. So basically, to show it differently, The signal can just be a straight line like this. So this is actually, so it's really bad drawing, I'm sorry for it. Never mind, this is the actual signal, but it can be something else. It can be, for example, a signal like this, okay? So in between the points, remember that you have no idea what's in between the points. You can have a really big spike like this, for example. This signal will have exactly the same sampled signal if we use 2 seconds as a sampling time, okay? So try to remember this because this is almost the only important thing you need to remember for what sampling means and what the sample signal is. So now, obviously, the sampling time also can affect the way that the sampled signal looks like. So if the sampling time is quite large, then you have fewer points. So it's the resolution is like losing some information. And then the opposite, if you have a sampling time like it's quite short, so high frequency sampling time, so high sampling frequency, then you have a lot of points and the information is not lost anymore. So here, this is just an animation. There's also the MATLAB code. All the MATLAB code will be given to the students. So I will just upload it to the TUVL. So here, if you can see, there's nothing really interesting. It's just like you can choose the sampling time. So in our exercise, it's 2, but if I specify something quite small, I've got more points, probably too many points. And if I say, for example, 10 seconds, you can see that I'm really losing information. I only got 4 points, so I cannot reconstruct the original signal. So here we have 2 seconds. So next is how can we define the UKTS? So here it's quite obvious. The UKTS is just taking the values at each sample. So the first sample is for k equals 0. Remember that the time started at 0 and not at 1. And then it's k times 2 seconds. So it's at 2 seconds and it's at 4 seconds and so on. And to find the Z transform, the first equation you got on one of the first equation of the lecture note is this one. So the U of Z, the Z transform of the signal is nothing else than the sampling point or the values at each sample times Z minus K, and K being the same as the sample number you're considering. So for example, here UKTS is defined. So U of Z, the first element of U of Z will be 0 because UKTS for k equals 0 is 0 times Z to the power 0. Then you got 2 times Z to the power minus 1 and so on. Here you can see that the Z transform will have infinitely many terms unless the signal converges to 0. So if the signal here was converging to 0, then at one point you got 0 times Z minus something and so on. So you can just skip all these terms. In here, our signal is not stopped at 30 seconds. I just show it for the first 30 seconds, but it's infinitely long. So it keeps being at 3 for until t equals infinity. So that means that this method gives you a U of Z that has infinitely many terms. So it's really good method to just have the beginning of the Z transform, but not all the terms. So to get all the terms, we're going to move to the second part, which is calculating the Z transform using kind of decomposing the signal into the time domain into simple function, and then identifying the Z transform of each function independently. So is there any question considering first this direct identification? Is everything clear? So I took a little bit of time to just go all about the sampling. It was probably quite obvious for some of you. So please let me know if you want me to go faster, slower, or anything else. So now we're going to see how to calculate the Z transform, as I said, decomposing the temporal signal or the time domain signal. So our signal looks like this, and we can decompose it into a set of, let's say, simple functions. So what I call simple functions is just a function that we know what the Z transform is. So if you look into the Formelsammlung, that is also on TUVL, so it should be this one. It's also on the lecture note. You got the so-called Z transform table, and you can see that there's a bunch of signals that are available. For example, ramp function here. You can have this one is not used that often. It's the step function. You also have exponential decay. You got sine wave, cosine wave, and so on. So if we can split our original signal into a set of this function here, then we have a direct identification into the into the Z transform. So to do that, let's just see this example. We can say that this original signal is first a ramp, so a ramp of unit slope, and then you need to add another ramp that is decreasing, so -1 in terms of slope, to kind of counteract the effect of the first ramp when you arrive at t equals 8 seconds. And then you got a negative ramp, which slope is 0.5, so -0.5, which is the blue one. And when you arrive at 20 seconds, you want this ramp to stop, so you need to create a fourth ramp, which is the opposite slope. So you just take a ramp whose slope is 1/2, the positive 1/2, to counteract the blue ramp effect. So here there's two main assumptions, is that each signal has no end, so you can start the signal whenever you want, but then it's gonna last forever. So you always need to create another one to counteract the effects of the first signal if you want to, if you want the first signal basically to stay bounded. And the second assumption is that you can shift the signal into positive time, so you can start the signal after 0. So for example, here U2 is started at 8 seconds, so it started at 4 times the sampling time. Once you have the function, so each function in the time domain, you know that you can Z transform each function individually because it's an addition of function, a summation of function. And we know that the Z transform of f plus g plus other function is the same as the Z transform of f plus the Z transform of g, and so on. So here we're going to use this property. So the only function we're using is the ramp function. So the ramp function, once again, it's in the table. You can see it here, the ramp function. It's always t is the sampling time. It's ts in our example, but here it's just written t. And this is the Z transform of ramp signal. And we also need to use a shift right theorem. So the shift right theorem is just saying that the signal is not starting at 0, but it's starting with an offset in terms of a number of samples. So it has to be a number of samples. So the offset is not on this table, but it's on the lecture note. Never mind, it's just this expression here. The Z transform of y, k minus nts with n being positive, r0, is nothing else than the Z transform of y times z to the power minus n. So if we know this, then we can just combine the shift right theorem with any function. In this case, we're combining it with the ramp function, and we end up with ts z to the minus n minus 1 over 1 minus z minus 1 squared, with n being the number of delay, so the number of samples from which the signal is delayed. So to express now each function into the Z domain, we're just going to transform it one by one. So for U1 is just a ramp, so it's obvious. You just have to replace TS by 2, because in our case, the sampling time is 2 seconds. And then for U2, you just apply the other, the kind of combined formula we have here. So the ramp function plus the shift right theorem. And you can find that is, you have here's a numerical application. It's Z to the power minus 1 times z to the power minus 4, because there's 4 sample delay, and you end up with minus 2z minus 5 and the same denominator. And so we can do it again for the U2 signal. So it's U3. Yeah, there's a mistake here. It should be U3, where is it here? Here it's U3, never mind. And you can also do it for U4, where I also forget to write the right one, U4. And in the end, you can see that the denominator is the same for all these functions, and we can add this function together, as we've just seen in the last slide. And so we end up with a Z transform this time, which is what we call a closed form solution. So this method will always give you a closed form expression of the Z transform of any signal as soon as you're able to decompose it into simple functions, okay? If you cannot decompose it into functions that are in this table here, then you will not be able to use this method. So this table is not exhaustive. There's other signals that you can use, but still you need to remember that you need to decompose into something that you know how to Z transform. So then there's a couple of other methods to do it. So the first question that was asked in the exercise was how could we go from UZ to the time domain? So basically here it means that how can we check that our Z transform expression we got here on the bottom right is correct. So the first method is to do exactly the opposite as what we've just been doing. Just removing this. So basically you take the Z transform, you expand it into, or you split it into simple fractions, so what we call simple element decomposition or simple fraction decomposition, and then you compute the inverse Z transform this time. So in terms of computing the Z transform, you compute the inverse Z transform, once again using the table, and you can get back to the T or the time domain signal. So I'm not going to do it here because it's exactly the opposite. So it's exactly the opposite as this slide. So you just start from the bottom right, and then you compute, you inverse the transform of each element, and you compute U4, U3, U2, and U1. Anyway, we're going to see that in the second example. The second method that can be used is a computational method. So computational method is not it's not going to give you a closed form solution, but you just need to compute, or you're going to compute the term one after another. So for that, first, it's a kind of a trick, but we are considering that the Z transform of the inputs, so of the input of the signal, sorry, so Z U of T is nothing else than a transfer function. So it's a transfer function whose fictitious input is omega, and omega is nothing else, it's going to be written here, omega is nothing else than a step response. So this is exactly the same as in continuous time. When you have a system, or when you have a signal in the S domain and you apply and you consider that it's a transfer function, then if you apply the Dirac, so a delta input, then you find this signal. So here we say that Z U of T is a transfer function and omega or W is an impulse. And so the impulse response of this fictitious transfer function has to be U of T or U of KT. So if we just take everything or keep everything in mind, if we just transform the denominator into this form, then we can put the denominator on the left-hand side and the numerator on the right-hand side. Here, once again, we're looking for U of Z. We don't know what it is, we need to find it. And omega or W of Z is just a Dirac, it's just an impulse, so we perfectly know what it is. If we go in the table, a Dirac, it's the first line, it's just 1. The Z transform of W in our case will just be 1. So then we can continue and we can write that UZ, we can just basically expand on each side. So we got UZ minus 2, UZ times Z minus 1, and so on. So UZ time function of Z and negative power of Z is equal to omega times negative power of Z. And so this is just using the right shift theorem. This is just shifted version of the signal. So now we're transforming U of Z is nothing else than UKTS. Okay, so U of Z is in the frequency domain. UKTS, it's the time domain in discrete time. And here we can say that U of Z is directly UKTS. And this second term here, so minus 2 UC times Z minus 1 is minus 2 times our signal, which is taken at K minus 1 TS. So it's a shifted version of the signal, which is just the previous value of the signal. And then we do the same for UZ times Z minus 2, which is not the previous value, but the value even before. So here, the goal with this computational method is to find UKTS using the previous value of UKTS and the previous value of the input, which in our case is a Dirac impulse, so we perfectly know what it is. So the goal of the computational method is always the same, is to find UKTS, so the signal at the step K is a function of the signal at previous steps and the input at previous steps. You can also sometimes include what we call direct fit through, which is going to be d beta times omega at the same input. So you can also find this, okay? So this term means that the current input is affecting the current output in our system. So here there's no direct fit through anyway, so we're just going to keep this formula here, and we're going to construct a table. So for the first line of the table, we know that omega or WKTS is equal to 1 at k when k is equal to 0 because it's a Dirac impulse. And so we can compute the first input. So the first input is on the first sample of the signal u, is a function of previous value of u and previous value of w. But before 0, when time is negative, everything is 0. So that means that u of 0 ts, so the first sample has to be 0. Then you can compute the signal as at 1, so the second sample, so k equals 1 is the second sample. So 1 times ts, you're just going to use the difference equation we got on top. So this is called a difference equation in discrete time. And so you just have to plug in the numbers. So uk minus 1 is 0 because it's u 0 ts, we just said it's 0. And then you just add uk minus 2 is a negative time, so it's also 0. And for the w, you only have to take wk minus 1, which is 1, because everything else is 0. And so you end up finding that u of 1 ts is 2. And then you can, using this formula, use the difference equation one step after another until you find all the different values. So here, as you can see, if you want to compute u of 1 million times ts, so the 1,000,001 sample, then you need to compute the 1 million values before. So it's going to take a lot of time. This is why this method is not a closed form solution. It's just approximating the UKTS, so the signal in the time domain, one sample after another. The only trick that you can use, so here I've been using it, is that after quite some while, here as the input is on your Dirac, you can see that the input is 1 at the beginning here, and then all here, it's all going to be 0 until infinity. And so you can find a kind of pattern into the expression into line 12, 13, and 14. You can see that these two terms, so mostly uk minus 1 and uk minus 2, are always going to be 3, and UKTS is also always 3. So that means that here we kind of convergence, if you want. So our signal will be 3 forever. This is not the case every time you're using this method, so be careful. This is just here a specific case where we get lucky and we can find a simple pattern that says that the signal will be constant. Most of the time, if the signal is not constant, then you will have to compute it forever. So if you want u of 1 million times ts, so 1,000,001 sample, you need to compute all the terms before. Eventually, after doing this, we have the original sampled signal, obviously. So when we use computational method, we got we don't compute an approximate solution, we compute the exact UKTS. Only problem is that it's taking quite some time. So here I also done it in Excel just to give you an overview if it's opening. So here you can see that you got the UKTs that we're finding. The W of KT is just a Dirac impulse, so it's just the 1 at time 0, so 0 times KTS. And then here it's just some formulas. So for example, in this case here, it's just omega or the input k minus 1, so it's this value here, and so on. And in here, you can see that you can quickly compute the signal in time domain if you got the difference equation. So difference equation, remember, it's the equation on the top here. And you can also compute any output. So for our fictitious transfer function, if I put a 2 here, then I'm computing the output not of a Dirac input, but a Dirac at 0 plus 2 times the Dirac shifted by 1 sample. Never mind, it's just to show that the computational method is a method that is that you can use when you got a transfer function in the Z domain to find the output in the time domain, in the discrete time domain. And then there's a third method, which is called direct diffusion method. So this method is, it's more or less the same as for the computational method. You're going to compute the term one after another. So if you want to compute all the full solution, whether you find some pattern into the solution, whether you need to compute all the terms. So it's infinitely long, basically. So this method is just, we've got the Z a transform of u of t is a fraction, so it's a ratio of two polynomial into z minus 1 power, or z minus 1 minus 2, so negative power of z. And so the idea is just to compute this division. So to compute it term by term to approximate the beginning of the solution. So here I've just constructed a table. There's other method to do it. It's just that this one is quite a good visualization, I guess. So on the top, you've got minus 1, minus 2, minus 3 is the power of z. And then you got the coefficients. So here we've got 4 coefficient. We've got 2 times z minus 1. So I plug in the 2. Then you got minus 2z minus 5, minus 1z minus 6, and 1z minus 11. And then we have our numerator. So our numerator, I just expand it into 1 minus 2z minus 1 plus z minus 2. It's not written, but the denominator is here. It's coming here to this term here. And if I want to remove the first term from my numerators, the first term is 2z minus 1. I need to multiply the denominator by 2z minus 1. And if I do so, the first term I'm going to remove is 2z minus 1. So the first term of this division here will be 2z minus 1. This is 2z minus 1 plus something else. And so first we're going to remove 2z minus 1. So if we remove 2z minus 1 times the denominator, we're going to remove everything as a power of z minus 1, which is quite okay. And then we're going to add something to the z minus 2 and add something to the z minus 3. That's why the table, we need to add 4 and minus 2. And so then we're going to look at what is the second term that we need to remove. And so the second term is 4 times z minus 2. It's here, it's 4 times z minus 2. And so to remove 4 times z minus 2, we're just going to multiply the denominator by 4z minus 2. As simply as this. And then we repeat the process. If we remove everything to the power of z minus 2, now we need to add some coefficient to the z minus 3 and to the z minus 4. And so we add everything, we sum everything, and we have now a numerator that is, or the remaining numerator is a function of z minus 3, minus 4, and so on. And so if we do this recursively again and again, we're able to find all the coefficients and we're able to approximate this division. So on the bottom, you can see that the division is now an approximation. So here I computed it up until the term z minus 10. And so this is what the direct division method is doing. It's just doing an Euclidean classical division. So it's only give you the solution term, one term after another. So once again, if you want to find UKT, or if you want to find the z minus 100, then you need to find all the terms in before, so it's taking quite some long. If you only want to find the first term, so d minus 1, minus 2, and so on, it's quite fast and it can be quite useful. Here, once again, we can see in the table, so you can do it at home if you want, but at the end, we're always going to have this pattern. So here it's going to repeat minus 3, 3, and so on. Okay, so this is why here we can be sure that after, so all the power of z that are lower than minus 10, so z minus 11, minus 12, and so on, will all be multiplied by 3. But once again, this is a specific case because our signal is constant after 30 seconds. So after 10 sample time. So after 20 seconds. And so from this, we're going to use the opposite as what we've been using at the beginning to compute the z transform with the direct method. Here we have a z transform that is directly a function of z minus 1, minus 2, and so on. So we can just back transform it into UKTS. So basically UKTS here, it's directly the coefficient that we find. So for example, U of 2TS is the coefficient just before z minus 2, so it's 4. U of 7TS is the coefficient before z minus 7, so it's 6, and so on. And we also have this special case where we know that after quite some while we identify that it's always going to be 3. That is not always going to be true. So is there any question now concerning this first exercise, so going from discrete to continuous time and continuous time to discrete time? So if there's no question, we're going to go through the first question for today, which is referring to the first exercise. So this question is a kind of summary of all the methods we've seen before. It's probably not that simple to answer. The only thing I'll ask you to do is trying really to answer it. Okay, so try to find the right solution. It's really good, I guess, indicator for you to see if you understood something, most of it, if there's something that you don't understand at all. And it's also good feedback for me to see if I need to provide some further explanation about one method or one specific point of this first exercise. So the question is, I cannot see it. Okay. The question is, you have a continuous signal y of t, okay? So y of t can be something, it's something continuous, can be, for example, this can be y of t, whatever. And you don't know what y of t is, okay? So here I just drew something, but you have no idea what y of t is. The only thing you know is that if you sample y of t, so if I take my signal here and I sample it, so remember that sampling is just taking some points on the signal. So here I can take a bunch of points like this. Then you end up with the graph on the right. So you end up with the graph on the right where you have a collection of points, which is just the continuous signal that is sampled at 1 second. This signal is only shown from 0 to 20 seconds. We can assume that everything else after is 0 if you want. The goal here is to find the correct proposition concerning the initial continuous signal, not the discrete signal. So is the continuous signal a periodic signal? This is the first answer. The second answer is that the Z transform with Ts equals 1 second starts as follows. So y here it's called y of kts is equal to 0.611, 0.60, and so on. The third answer is that the Z transform with Ts equals 5 seconds. So if instead of taking 1 second, we've been taking 5 seconds, then the Z transform of this signal will have been 0. So 0, 0, 0 at each sample. And the fourth answer is that the average value of the continuous signal, so not y of kts, but y of t, has to be 0. So its average value, we can be sure that it's 0. So at this point, I wanted to share a poll that for reason I don't know, it's not working. So can I do it from here? Okay, thank you, Peng. So here you have the poll. The poll is anonymous, so please take time to try to figure it out which, there's only one correct answer, and try to figure out which answer is the right one. So can you see the poll, first of it? Yes. Okay. So please take time and try to, take time yet. Try to take a couple of seconds and just answer A, B, C, or D. It's once again, it's anonymous. It's just for me to get some feedback. And if everyone got the correct answer, we can go to the second exercise. If it's more tricky to find the right answer, then I can provide more explanation. And we can also have a discussion of what is not clear and whatever. So most of you answered or choose the answer C, which is the correct one. Some of you answered the answer B. So the second one, yeah, I've just written A, B, C, D, it's 1, 2, 3, 4. Yeah, never mind. The first one, first of all, yeah, of course it's wrong because, as I mentioned, we don't know what the signal is. So in between the points, if I just take the pen, in between the points, we can have anything. So here, some will assume that we have a nice sinusoid into continuous time. This is one possibility, but it can also be something completely different. Sorry. It can, for example, start with a sinusoid like this, and then here do this. This is completely right to do this. I can do another one. And so this is not, this has not an average value of 0. Okay, so also some of you have the first answer. So is anyone who answered said that it is a periodic signal? Can anyone explain why it is a periodic signal or why it is not? Because it is not. So did someone answer question A and now understand that it cannot be a periodic signal? Is it clear, or should I just go into more details why we cannot say that the y of t is in the periodic signal? So we cannot say that it's a periodic signal. I mean, it could be a periodic signal, but it could also be something else. Okay, so we just have some points, we just have some sample, and we have no idea what's in between. And this is the most important part to understand, that we have no idea what's in between the points. And for the second answer, some also, so one person answered the second answer. The second one was, it was just a kind of tricky answer. It's not fully correct because the first sample is at k equals 0. So this is the first sample. And I've just added this answer not to trick you, but it's just because it's a common mistake to forget that the first sample of a signal is at k equals 0. So remember that always second sample is k equals 1, and there's always a shift between the sample index, let's say, and the k value. So remember, first sample at 0. Okay, so it was not that bad. I mean, most of you, so if we just take the answer, you were 7 answering the correct solution. So unless you have some more question, we can move in, I guess, to the second exercise. It's already 45 minutes. Yeah, the second exercise a little bit shorter, I guess. So is there any question, remarks? Also, the way I'm proceeding into the solution, is it too fast, too slow, or just tells if there's anything that you wish to be different or whatever?
I have a question concerning answer 2.
Yeah.
These numbers 0.6, 11, 0.6, and so on, these refer only to the coefficients, or is it meant to be only this, the z transform? Because then the z to the power of whatever is missing, or?
So here, for the second answer, we've got y of kts. I don't have space to write. So the answer is that y of kts is equal to, so the z transform of the original signal at ts equals 1 second is equal to 0.6. So it's, if I have to write it, it's going to be like 0.6, and it's going to be 1, 1, 0.6. So you see that it's almost the same signal at this one, but the only mistake here is that the first sample has to be 0. So here, the correct answer will start at 0, comma, and then 0.6, and so on. And as we've just seen before, if we have the coefficient, we know that the z transform of y of t is equal to the summation of y of kts times z minus k. Okay, so if we know this is k, if we know this, so this is not the correct one, but if we had the correct one, we can also identify the z transform of y of t. I don't know if that was your question. If now it's clear.
Yes, thank you. I was wondering where this z to the power of minus k went to, but yeah, per definition, yeah.
So here there's really two things. The first thing is, this is a sample signal, this is a continuous signal. So here, if you got all the coefficient one after another, you basically got this sequence here, which is a discrete signal. And if you know the discrete signal, you can compute the z transform using this equation here, okay? So there's two things, and of course the coefficient are the sequence. So y of kts are each element of y kts is a coefficient of the z transform. Okay. Is there any other question regarding this first exercise? Also, this we're gonna go back into we're gonna see all this method again in exercise 2 and in the next lectures or next exercises. But still, it's really important that you have a good understanding of how to switch from continuous to discrete time, and also the fact that if you got only the sample points like here, you have no idea what is the exact continuous signal, that the original continuous signal. You only know that it's going through all the points. So you can just, it's equivalent to the game of connect the dots. So you just have to connect the dots, but you don't know how to connect the dots, okay? So intuitively, you will connect it this way, which makes sense, but it can be something else. So if everything is clear, now we can, I guess, go to the second exercise. So is there any other question? So otherwise, we're going to go to the second exercise. So second exercise that was proposed The second exercise, we don't know what the continuous signal is. We only have the Z transform of a signal. So we have a Z transform of X. So we write it capital X because it's a Z transform. It's the same as in the Laplace domain. And we don't even know the sampling time. So the only thing that we can find is the time sequence of XKTS. That means that we have a continuous signal that is called, let's call it X of t. Then someone just sampled it at sampling time TS. We don't know what TS is. We don't know what the continuous signal is. So this is not known. And then what we are given is only the discrete not even the discrete representation that we can find, but we are given just X of Z, okay? So the only thing we can find now is X of KTS, okay? And from X of KTS, as we don't know TS, we are not able to find X of T. Of course, first, because we don't know the sampling time, and second, because we know that in between the points, it's completely unknown. So here's the goal, finding XKTS. The first method that we're going to use is partial fraction expansion. It's exactly what we did in the first example, but here in the opposite direction, let's say. So we start from X of Z, we transform it into a sum of partial fractions, simple element, and then we go back into the time domain. So here is our expression. And so to find XKT of S, the first method is, first, we're going to split X of Z into simple elements. And the goal is, once again, to find simple elements that are on this table here. And if we can identify a collection of elements that we can identify in this table, we can quickly look at the X of T or X of KT, okay? So to do that, the question is, remember that for the time domain, if you have a signal, so for example, like this, then we can say that this is our first element here, this is our second element, and these kind of exponential decay, the third element. Here we have X of Z, so we don't have this kind of representation. So we need to use the partial fraction decomposition that I guess you already know from basics of control or any other equivalent courses, because it's exactly the same when you have Laplace signal in the Laplace domain and you want to find it into the time domain, then you need to use the partial fraction decomposition or partial fraction expansion, depending on the name. So here, first step, so this is the only difference between the discrete time analysis and the continuous time, is that before doing the partial fraction decomposition, we're going to divide the signal by Z. So why are we dividing the signal by Z? So you see that I'm dividing on the left and also on the right, so the Z on the right is also vanishing. Then we do it, it's just a trick. It's just a trick so that if we do the expansion, partial fraction expansion now with this expression and then multiply it by Z again, we will be able to directly identify some of the terms that are here, okay? So if we just do that as it's proposed, then we can find X of Z over Z as two terms. So 1 divided by Z, Z squared minus Z plus 1, and Y divided by Z plus 1. So here, I don't know if you're all comfortable with partial fraction expansion, but this is exactly the same in continuous time. So we're just identifying fractions whose denominator, so denominator here, for example, Z plus 1, has to be only one pole, okay? So it has to be one pole. So if it's a real one, or two complex conjugate poles, okay? Eventually, you can also have a multiplicity of poles. So you can, for example, have C plus 1 to the cube if you got multiple real poles at the same location or multiple complex poles at the same location. So is there any question regarding partial fraction? Because I guess you already know it, so I don't want to spend that too much time about it. If there's any question, just say it and I can give some more details. I can also give you some PDF documents if you want, explaining this a little bit further. So then there's nothing interesting, so I'm going to be really fast. You can just do it at home. We've got an expression here. So we've got this, okay? And we know that this here is equal to this. So we just have a set of equations. We want to find A, B, and C. It's just direct identification. we can have a linear system of equation of A, C, and B, and so we can find A, B, and C at the end, which is A will be equal to minus C, C will be equal to, it's not even written here, it's probably on the next slide. So A, B, and C. So we've got, if I remember well, it was A Z plus B. So A is equal to 2 over 3, B is equal to minus 1 over 3, and C is equal to minus 2 over 3. Okay, so never mind, just do it at home. It's just a little bit of mathematics involved. And then we find xz over z. So the next step obviously is to multiply by z. Okay, it's not written, I should have included it, but we just multiply by z because we're interested in x of z and not x of z over z. Then the next step will be to identify here on the table, you see that it's always negative power of z, whereas here we got positive value of z. So we're just gonna make everything, so kind of express it into negative power of z. So for example, the first term we divide by z square, and the second term we divide it also by z square, and by z only. And so we have only negative power of z. And then from here, we can identify terms into the z table here. Sorry, we can identify terms into the z table, one term after another. So the first term can be identified, the second one, and you remember that the z transform, the inverse z transform of f of z, sorry, should be capital letters, uppercase here. So f of z plus g of z is the inverse transform of f of z plus the inverse transform of gj of z. Okay, so this is exactly what we're going to do, and we can say that this is f and this is g or j. Okay, so the second term first, because it's simpler, we can directly identify exponential minus akt, which is here. So it's 1 over 1 minus exponential minus a times the sampling time z minus 1. So it's basically something in the form 1 minus some coefficient, let's call it gamma z minus 1. And this is exactly what we have here. We have 1 over 1 minus a z minus 1. And so we can say that the a term in the table would be equivalent to the exponential minus a to the sampling time. So we can say that it's just minus 2/3 of a to the power k. Okay. And we can do the same for the other term. The thing is, the other term is a little bit trickier to identify, but it's just a cosine form. So if we go on the table and look for the cosine form to this one, we can see that we got 1 minus z minus 1 times the coefficient, which is cosine of omega times the sampling time, divided by 1 minus 2 times z minus 1 times the same coefficient. So here, if we go back here, we can see that we've got, so we can rewrite the expression so that it's a little bit more obvious, but you can see that here I've got minus a half times z minus 1, and here I got minus 2 times 2 times minus a half times z minus 1. So it's the right form for our cosine solution. And we just have to apply the formula, and we find that it's 2/3 of cosine k omega times the sampling time. And so cosine of omega ts has to be 1/2. Okay, so it has to be 1/2 because in our expression we got here minus 1/2. And in the table, it's minus, where is it? It's this one, it's minus c minus 1 times cosine omega t. So omega t, cosine omega t has to be, in our case, minus 1/2. So here we've got our two part of the signal. We can reconstruct the full signal. So xkts has to be equal to 2/3 of cosine pi over 3k minus 2/3 minus 1k. Okay, and this is cosine pi over 3k because it was equal to 1/2 basically. And as you can see, I've just made the representation. So the only thing we can recover from the x of z is x of kts. So it's not the continuous signal, it's only the samples of this signal. And we don't know the sampling time. So here we are as a function of k and not a function of t, because ts is unknown. Okay. So this is really important. If you are given a sample signal or a z transform of a signal, you should know what TS is. If you don't know what TS is, you can only express it as a function of k, so a function of the sample, basically, not a function of time. Then there's a second method, is called the direct division, and we've already seen it, so I'm just going to go quite fast about this method. So you have z to the z minus 1 divided by z plus 1, d squared minus z plus 1. This is what is given in the PDF. You can rewrite this as z minus 1 minus z minus 2 divided by 1 plus z minus 3, which is the form of the coefficient is a little bit easier to work with to compute the division, and then you can compute the division. So here's the division. I haven't computed it. I mean, I computed it, but it's not on the PowerPoint because it's exactly the same method. First, you multiply 1 plus z minus 3. So you take 1 plus z minus 3 times the first element here, which is z minus 1. And that means that you're removing 1 times z minus 1. And 1 times z minus 1 is the first coefficient in our numerator. And so you're just removing terms after another and adding also what you removed for higher power of z minus something. And you end up with this sequence here. And as you know this sequence, then you can use x of z is equal to xkts z minus k, and you can identify xkts. Okay, so here first element z minus 1 will be this one, z minus 8 will be somewhere here, I guess, and so on. So it's a direct division method. Once again, you can compute it, but it's taking quite some time. So it's okay for the first samples, but here, if someone asks you for 1000 TS, then you have to compute this term until d to the power minus 1000. So you see that it's going to take quite a lot of time compared to the method using the table, identifying the terms in the table. Okay. So first to compute the first terms of the temporal sample signal or sample signal in the time domain, but it's not efficient to compute xk of TS for a large k. Okay. Also, we can find some recurrence in the solution. You can see that. So here it's only the first term, but if I split it here up until to there, it should be 0, I guess. Then you can see that this is just repeating over and over, but it's not that obvious, and it's usually not that easy to find a repetition like this. And a repetition appears only if the signal is periodic, obviously. The last method is the computational method. So the computational method, we've already seen it also before. So as you remember, it's only computing terms one after another. So it's quite fast for the first samples, but it's a little bit more difficult if you want a lot of samples, or if you want the full solution, then it's going to be infinitely many time, unless you can, once again, find that the signal is periodic and so find a pattern into the solution. So you remember we said that x of z is a fictitious transfer function whose input is just a Dirac. So delta 0 of z is equal to 1. Then everything we've already seen it. We just once again apply the transformation for x of z. So it's not a transformation, it's just we expand both terms and we just write it as a function of a negative power in z. And then we have from this the difference equation. So here there's no step, so I can probably give a little bit more information. We've got x of z is equal to z minus 1 plus z minus 2 divided by 1 plus z minus 3. And then what you can do is put everything on the left and on the right. So it's, it's 1 plus z minus 3 on the left-hand side. And on the right-hand side, it's equal to z minus 1 plus z minus 2 times omega of z, okay? Or w of z, never mind. And this is just a Dirac. So just an impulse response, which is equal to 1. And then here you can say that this is equivalent. So the first term will be x of kts plus x of k minus 3 ts. Okay, remember the shift right theorem. We've got z minus 3. So this term multiplying x of z is equivalent to taking the signal 3 sample before. And on the right hand side, it's the same. Here it will be like t minus 1, and here it will be the Dirac at t minus 2. And so you end up with this equation on the bottom where you got xk of ts So then you can Z transform everything. And so this is the Z transform of X of Z times 1. And then you have to Z transform the terms into these parentheses here. And you find exactly what I found here. So minus xk minus 3ts plus omega or w k minus 1ts plus w k minus 2ts. Okay. So is this method clear? Because this method of finding a difference equation is really important, because in the Laplace domain, so in the S domain, we've got ordinary differential equations. So you got like the output is the output and its derivative as a function of the input and its derivatives. Here you got the, so I'm just gonna make it clear because it's really important. In the S domain, you got like y dot, y double dot, and so on as a function of u dot, u double dot, and so on. Here into the Z domain, we've got what we call difference equation. So difference equation, and the difference equation is nothing else than y, so y of kt, y of k minus 1t, and so on, will be a function of u of kt, so t is ts, u of k minus 1 ts, and so on. Okay, so in the discrete time, it's really easy. X of kts is a function of the previous value of the signal x and the previous value of the input. So here's the input is w. Also, you can have the current input once again, but here it's not the case. So let's keep this direct fit through for now on. Once you have this, once again, exactly the same as last time, you have the difference equation and you can just compute it term by term, one after another. And if I open it in Excel, it's almost the same Excel file, the same input. It's a Dirac function. So 1 at k equals 0, and then it's always 0. And you need 3 terms. You need x at k minus 3, you need omega at k minus 1, and omega at k minus 2. So x at k minus 3 will start here. It has to be 0 because it's before time, it's for negative time. And then while you're here, you see it's the first element, and then it's just a repetition, second element, and so on. But anyway, we'll also have this Excel file. And then the omega is just shifted version of omega. So shifted by 1 sample is 1 here, and shifted by 2 samples is 1 here, and then you've got the solution. Okay. And so here you can find the solution. So 0, 1, minus 1, 0, minus 1, which is exactly the same as the one we've computed before. Okay. So just before the question, just going to go back here. So just as a reminder, the partial fraction expansion, we're just identifying these functions. So we're identifying the function for the full signal, let's say. So for all the samples at once, it has to be possible. Sometimes it's really hard to find, but if we can't find it, then we have all the samples. Direct division method, we're finding the samples one after another, which is also an exact solution, but you need to compute for the number of samples you need. So it can be quite large. And computational method is also the exact solution, but you need to compute one sample after another. So sometimes it can take a lot of time. Okay. Here, if I want X of 1000 TS, once again, you need 1000 line, which is taking quite some time. So is there any question regarding this second exercise? And as you've seen, the second exercise is mostly the same as the first exercise. It's the same method that we've been working through. So if there's no question, we're going to go to the second question for today. So using this method, so the Z transform table, this method here, the computational method, so computational method, you're computing samples one after another, and the direct division method, we can transform a signal from the Z domain to the time domain. So you can have U of Z to U of KTS. And so there is once again only one correct answer. So all these methods lead to the same results. Only the direct division method gives a closed form expression, so a finite representation of U of KTS. Using the Z transform table, it is always simple to find a solution. And with the computational method, we can find a continuous solution U of t. So here you once again have the poll. So also please take some time to think about it. This question is really simple. So some will be more complex in the future. This one is quite simple, but it's really important that you find the correct answer, and also you can you understand why the other answers are not correct. Okay, so even if you find the correct answer, try to analyze why the others are not correct. It may look completely obvious if you understood everything, and I guess it's the case. Otherwise, we can also have some further explanation. So now we have the answer. So most of you answered the first. So choose all these methods. It's the same result. And some of you answered the second one. So that's quite nice because the answer is obviously the first one. So just really quickly, because nobody made the mistakes, but just for further explanation, the last one is wrong because we cannot find U of t, as I mentioned before, can only find U of kt. The third one is wrong because using the Z transform table, if you have a Z expression or a Z, a signal into the Z representation of a signal into the Z domain is not in the list here, then you're kind of stuck. You cannot find it into the X of t. So this table is not exhaustive. There's other signals that are well known, but still sometimes it's quite tricky. The second, so the first method was correct. You always gonna find the exact solution. It's just a matter of, are you finding it for all the samples at once, or are you kind of finding one sample after another? And the second method, so can anyone who answered the second method explain why he or she thinks that this is the correct answer? Or can anyone who answered the first answer and perfectly know that it's not true express why it is not true? So why this is not true or not correct? So it's not correct because the direct division method is most of the time not giving a closed form expression. So if we just go a little bit backward into, I guess it was the last one, not the computational method. So if we just go from the second exercise, sorry, it was after this. So here, direct division method. So I don't provide a lot of details, never mind. So you can see that here, for those who made the mistakes, that when we're dividing z plus 1 by z squared minus z plus 1, so when we're dividing, it's the same expression, but when we're dividing these two polynomials, we don't have a closed form solution, okay? The z elements here, as you can see on the representation, that it's not here, but if we take the representation of xkts from the timetables, from the z transformation table, then you can see that it's never ending, okay? You will have points forever. Here, there's probably another point, let me think here, and then there will be another points at 0 here and then here. So that means that the solution of the division of these two polynomials is not going to be a bounded number of coefficients. It's going to be infinitely many z to the negative power terms, okay? The only thing that I said is that here we can identify that there is a pattern, so we can see it here a little bit. If you take, sorry, these points here with the pen, if you take all of this plus this one, this is just a repeating again and again. So this is the first, and then this is exactly the same pattern here. So you can identify that it looks like it's repeating. And so you can say that this is a periodic signal. And so only computing the first terms, then you can find with division of the two polynomials that you will have a repetition that will be here. So here it will repeat the first terms up until probably this one. or something like this. Okay, so it's not a closed form solution, that division method, but it can be sometimes. It can be if you make some identification. Cannot remove this. Is there any other questions? So regarding this question or regarding the stream method we've seen here to go back from the Z transform expression to the time domain expression.
If no one has a question, could you go back to the partial fraction expansion?
Yep. And a second, I'm just trying to remove this markup, that it's not removing it anymore. Okay, then let's go back in the start it again. Okay, so partial fraction expansion.
Yeah, when we did the when we used the table to.
So partial fraction expansion is, it was here, right? There.
Yeah. No, the
yeah, I'm
expansion
stopping.
is fine, but just
Yeah,
the transformation back, because you use the exponential function. Or
which common?
No, a bit further.
So after this?
Yeah, after this, yeah.
Here?
So and then the next step.
Oh, so here.
Yeah. So we have, yeah, then we multiply by C.
Here we multiply by D, yeah.
Then we have C over, yeah, or 1 over 1 plus C minus 1. But shouldn't that be the very last entry in the table?
So for this term here, you mean for this one here, you mean?
Yeah, exactly.
So for this one, we identify it as some coefficient, let's call it B, not mistaken, and 1 plus Z minus 1, okay?
Yeah.
And so you are proposing to identify it as
the very last entry. And
this
then
one.
the A, yeah, with A equals minus 1.
This one is almost the same as this one, as you can see, okay? This one is just the same as the one on top, saying that minus exponential I80, we just write it as A, minus A, okay? If you can see, if you have minus A and you say it's minus exponential 80, we have the same. The only difference is, and you're right, is that here, so if I said I took this one, it's wrong because it just this one, 8 is okay, which is in the PowerPoint basically. So it's AK, it's not the other one.
Okay,
it's
okay.
AK because the sampling time is not part of the Z function. That's nice that you
I wasn't paying
because,
attention, sorry. I thought it was you used the exponential function.
No, and that's really nice that you pointed out, because on the right hand side, so here, the difference is that here the Z transform is a function of the sampling time, okay? Here the Z function is not a function of the sampling time, okay? So not a function of TS. So this is really, really important because it's two completely different signals, as you pointed out. Exponential, a decaying exponential, and a power series completely different. So that's a really important point. I haven't kind of emphasized it today, but the Z transform can be a function of sampling time or not. It depends. Okay.
Okay. Yeah. Thank you.
So for example, on the cosine, you see it's a function of sampling time. So you cannot see where the sampling time is hiding here, but it's basically hiding into a cosine term. Okay. Is there any other questions? Still, I can go through a quick conclusion and probably you will have some question thereafter. So everything is done, question is done. And so now the conclusion is just a summary of what we've seen today. So we started with a continuous signal, then we use sampling to sample the signal. Also, it's not seen in this session because there is no, I mean, when you've got a continuous signal and you know what is the sampling time, okay, doing or finding the sampled signal is there's only one solution to this problem, okay? This is, there's only one method to do it. It's just taking a point at every TS time. So TS second, if it's in second. In the other direction, as I already mentioned, if you got a collection of points like this, there's multiple methods that you can try to estimate the continuous time signal. You can only estimate it because you got no information of what's happening between the dots. You can have stuff like this, you can have this, whatever. So usually what we're doing, what MATLAB is doing is what's called first order hold. So you're just keeping the same derivatives. Let's say that there's a point at 0 here. Then if you just keep the derivative, you're just kind of, it's equivalent to connecting the dots, sorry. It has to be straight lines connecting the dots. So it's just a bunch of straight lines connecting the dots, okay? And we're going to see in the next session or the session after, anyway, we're going to see in the exercises that we're mostly going to use zero order hold. So zero order hold is just holding the value. So here we're going to hold the value at 0, then hold here, hold here, hold the value here, and so on. Why we're using the zero order hold? Because it looks like it's less interesting. I mean, the first order hold that then I can draw again in blue looks better solution, better approximation, but the blue method is not a causal method. So what means that it's not a causal method is that if I just take another point here, okay, so let's say that the real point will be, if I take in red pen here, if I'm currently here, so let's say I'm currently here, I have no idea where the other point is. So if I'm using the zero order hold, I'm just holding the value until I got a new point. If I'm not using the zero order hold, but I want to use the first order hold, the only thing I can do is keep the same derivative, okay? But I cannot say that this is the right one, this one, because I don't know where the next sample is. So that's why the zero order hold will be used. So now go back to the method we've seen today. So mostly what sampling is, going from sample to continuous signal is always tricky. We need to kind of estimate, interpolate the values. Then we've seen how to find UKTS is just looking at the sample values, and we've seen that we can compute the Z transform of the signal using the UKTS and this expression, so this summation, but it's an infinitely long terms of Z to the power minus something, so it's not a closed form solution. Then we've seen that from continuous time signal, you already all know how to do it. We can decompose the signal into simple functions. So here we just said that this is U1, then U2, U3 was like this, and U4, whatever, if you remember. And we can, of course, say that f of t is a collection of, so f1 plus f2 and so on. And we can use a table to go from the discrete time to the continuous time. As soon as we have on the left-hand side here, a collection of simple function as a function of time. And on the right-hand side, as soon as we have partial fraction, okay? So partial fraction is just simple fractions, so with only one real pole or one complex pole, or greater multiplicity. And finally, we've seen two methods to go from the discrete representation into, so the f of z, capital F of z, into the f of kts, sorry, f of kts. And to do that, we have the computational method and the direct division method. Also, we can use the tables as usual. So we can use these tables, but if we cannot use a table because it's the expression is too complex, or it's just a numerical approximation, then we still have this computational method and direct division method. And it's mostly what MATLAB is using when MATLAB is not able to find anything in the table. It's probably the computational method that is used, which is using the difference equation. So now we are heading to the end of this first exercise session. Yes, that was the end. So do you have any question regarding what we've seen in exercise 1 or 2? And do you have any comments or remarks about the proceedings, about how I'm going to give you the solution? And probably I should do it another way. I mean, you can still propose anything. There's anything, everything can be done basically, because this session is really for you to understand. So do you have any comments or remarks or whatever? So if there's nothing to say. We're right on time. It's 11:30. So we're perfectly on time. So this session will be available on YouTube anytime soon. And you will have, if you want to take part into the exercise part of this lecture, you will have to do these two exercises that are here. So you can find this document on TUVL. Okay, so I was already on the homework. So you can see that the first problem is more or less the same as the first exercise. It's the same question. And the second problem is also the same question as the second exercise. So if you wish to do this problem, do it and then upload it to TUVL within 2 weeks. And if you don't want to do the exercise part, I still encourage you to do these exercises as training. Okay, so now if there's no further questions, thank you for getting involved today, and see you next week for the second session.